This is the third part of the third online lecture series on measurement and validity, where we look particularly at internal and external validity. So the learning objectives for this part of the lecture series include understanding internal validity, a brief review, as we've already taken a look at some aspects of it, and also understanding more about external validity, or what's sometimes described as generalizability, so understanding how case selection affects descriptive and causal inference. So when we go back to our depiction of a theoretical system, we just looked in the last lecture at measurement validity, and internal validity is about the relationship between the independent and dependent variable. So again, whether or not we're sort of dealing with correlation, causality, and whether or not we really know if the independent variable does in fact cause a dependent variable. External validity, I have it graphically shown here, but really think about it as the extent to which we can generalize about the results from our study out to a broader population. So how much we can make claims about whether or not the results that we found apply in a range of contexts and a range of situations with a range of different people. So a precise definition of internal validity is the degree to which causal inferences made based on the study are likely to be valid. So again, the focus on internal validity is a causal inference. And what that means is that we need to be able to eliminate alternative explanations. Now, in general, if we think about three different types of studies, we can think about lab experiments, so experiments where a study where an experimenter has very tight control, which we'll be looking at in week 4, has quite potentially high internal validity, though there are some threats that, again, we'll be talking about in future weeks. If we talk about different types of quasi-experiments, so usually field experiments or survey experiments, these also have a pretty high potential internal validity. Again, if they're designed correctly, there are clear threats even then. Observational research, so survey research and other types of research where we simply observe what's going on and don't directly manipulate it, those are going to typically have a lower type of internal validity, though if we use something like longitudinal data, which allows us to incorporate time into the causal analysis, or in something like a causal network design, a Bayesian graph, which we discussed briefly in an earlier lecture, these can in fact increase the conviction that our study has higher internal validity. Just as a reminder, one of the biggest threats to internal validity that we face in observational research, and really other types of research as well, is the idea of a spurless correlation or a confound. So it's not the case, as we discussed before, that eating more ice cream is necessarily leading to an increase in drownings, but rather that an external factor, summer, is causing both. Similarly, police officers aren't leading to the crime rate, and high crime rate isn't causing people to necessarily hire more police, though it may be, but it's hard to make that inference because it could just be that in both cases, these are reflections of higher population density. Other threats to internal validity that are important, basically, again, in the process of trying to eliminate alternative explanations, if we have extraneous variables, it actually can bias many of our estimates. If we throw a bunch of extra stuff in, it might actually submerge the effect of the primary variables that we're talking about. Omitted variables can actually cause a type of bias. If you end up taking an advanced quantitative or econometrics course, you'll probably actually do the omitted variable bias proof that shows how your estimates are in fact biased if you omit a key explanatory variable. So that can really compromise the internal validity of your study. If you don't have temporal order right, this can again cause serious effects. So it could be that in the earlier case we looked at with runs scored and salary, we would really need to be thinking about the temporal order. So the point the salary is assigned is where we need to be assessing whether or not performance has an effect on later salary. We can't do them at the same time because the temporal ordering is just simply wrong. It's one of the reasons that over time data can actually help us get greater purchase on causality, even if they are observational, than not using longitudinal data. Other threats to internal validity are actually sampling, dropout, and non-response. Now, we typically think of these variables, these types of phenomena, sampling issues, dropout, or non-response, as threatening external validity, which we'll be talking about a little bit more in a moment. But there are some nice papers that show that, in fact, if there is some sort of a moderation effect, we can actually significantly either miss a causal effect altogether or at least get the wrong estimate, a biased estimate, because we have certain parts of our population on whom these variables have a different relationship missing from our sample. Measurement error can actually sneak in for much the same reason and affect internal validity, or at least the validity of our estimates of the relationship between our X and Y variables. Another thing that we have to think about is regression to the mean. Again, this can typically mean, in essence, that we might sometimes accidentally see a relationship that doesn't exist. We'll be talking about this a lot more in Statistics Week, but just to sort of flag some of the ways that internal validity can be compromised. There are quite a few additional specific threats to internal validity in experimental designs, and to some extent also will, in terms of biased measurement, and those are going to turn up in the survey design week, but we'll be returning to those in the future. Just keep in your mind that internal validity is something where we are trying to estimate a relationship or trying to understand the relationship between X and Y, and we might get it wrong. So we have to be on the lookout for these threats. Now, before we talk about external validity or generalizability, I want to briefly introduce some of the language around the ideas of samples and populations. If you've taken an introductory statistics course, this should all sound like review. If you haven't, then this will be some new material. It's not particularly complicated, but it's a very useful set of concepts, a technical vocabulary to keep in mind. So, we have our little population out in the world of all these people. These are our little green guys here on this graphic. Now, we can't go out, for example, and ask all 300 plus million people in the USA what their political attitudes are. What we can do is take a small sample, and then we want to try to make inferences from that sample out to the larger population. So sampling is simply the process of choosing a set number of units from a wider population. Again, this is another slight depiction. We have the same idea. We have a sample, which is some little small n, right? These are the number of units that is going to represent this larger group. And the population, which is going to be our big N here, it's all the units in the population that we're interested in. Now, one thing I want to stress is that it's not like the population is in the population of America. It could be any population we're interested in. Maybe we're interested in school children, ages 6 to 9. That's our population of interest. Maybe we're only interested in American school children, age 6 to 9. We need to be clear, because the way we would study all school children and the way we would sample from that and the way we would study American school children might be slightly different. Now, it could be that we could make inferences from American school children age 6 to 9 to other school children in the developed world, but maybe we couldn't make inferences about how the same type of study might play out in the less developed countries, or might have played out in the 15th century. So again, being clear about what the population of interest is. Maybe you're interested in all companies. Maybe you're interested in only Fortune 500 companies. Maybe you're interested in understanding the incumbency effect in congressional races, or maybe you're interested in the incumbency effect in local campaign races. Or maybe you're interested in all elections, in which case you would have to think about the differences between the local campaigns, national campaigns, maybe the Senate versus the House, maybe even the presidential race, right? So in each case, you have to be clear about your population of interest, and then you think about the sample you're going to take from it. In the end, a big question is the inference generalizable? I.e., are the things that we're going to make on the basis of studying our sample something we can make a claim about to a larger population? And how large is that population will depend on how good of a sample we have from that population. So here we have a simple random sampling method. This is a government income tax auditor, of whom we assume there are at least some that still exist. And they have a set number of tax returns they need to audit. So they have a list of them all. They generate a random number. Maybe they're just using Excel even to just generate their random number. Maybe they're literally flipping a coin. The problem is that's only going to give them a 50-50 chance. So they need something that, say, maybe they roll a dice if they need 1 in 6. These are all random sampling methods where, in essence, you just say, okay, I'm going to sample. I'm going to assign everyone a random number between 0 and 1. And then I am going to choose the 5 lowest or the 6 lowest. And those are going to be the people that I actually go and audit. And one can actually calculate, as you can see from the formula here, the probability of being chosen given what we know about the sample size and the population size. The basic premise of simple random sampling is that units have an equal probability to be selected. So we could think about if we had a telephone book, we could just go through and say, okay, we're just going to choose randomly assign everyone in the telephone book a number, and then we'll choose, you know, the 1,000 lowest numbers, and those are the people we go and survey. Now, what's difficult is that the sampling frame we're using here, maybe the population we're interested in is all Americans in a particular city, but the sampling frame that we have here is in fact the people in the phone book. And while that might have at some point been fairly good representation of the entire population of the city, at this point it might be not a very good representation because people keep their name out of the phone book or because they're using mobile phones instead of a fixed landline. But again, leaving that aside right now, simple random sampling is simply a purely just p probability. And you can again see some of the math. If you've taken statistics, it should look familiar. All you need to know is that the probability of being chosen is p, in essence. Okay. So those are what are called simple random sampling is an example of a probability-based sampling strategy. There are others though. So in the phone book example, maybe what we need to do is, okay, we're trying to get a good sample of all of the United States. And so what we need to do is first select a certain number of phone books, right? And then we select people from the phone book. So we need to stratify our sampling first by phone book. But maybe we don't want to have each city. So maybe we've got a lot of phone books from small rural areas and New York City, right? And San Francisco and Los Angeles and Miami. We don't have as many phone books from these very large cities. So we might need to stratify an additional step. And we might just say, okay, we're going to choose 2 of the phone books from these large urban areas, and we're going to choose 2 phone books from moderate urban areas and 2 phone books from small rural areas, and then we'll choose a certain number of people from each of those. So that would be an example of a stratified sampling. And the same type of sampling can be done for something called cluster sampling. These are much more advanced. If you do any survey work, if you take the survey research course here at UMass, I think there will be one offered next term, then you can learn more about these different sampling methods, probability-based sampling. There are, though, non-probability-based sampling strategies, and you may, in fact, be using those on your group project in this class. Convenient sampling, i.e., let's just stick something up on the internet and get a bunch of our friends at UMass to respond, is something that is often used in certain studies. Now, there are limits that we have if we use a convenient sample. We can't necessarily make the same claims about how accurate we can't generalize out to the entire population of the US the way if we used a probability-based method that started off with a good sampling frame that actually represented the United States. So with convenient sampling, though, it can be quite useful. We might use, say, MTurk, which has a decent sampling frame that it's taken from. It's a little bit young. It's a little bit overeducated. It actually can skew often a little bit male and Republican, which is sort of the opposite of what we get with a lot of face-to-face phone calls. But it can be a way, especially if you're running something like a survey experiment, to get a decent random assignment of a wider range of people than if you just conducted the same experiment with first-year college freshmen. The sampling frame is certainly larger, so you feel a little bit more confident that your experimental results generalize out to a larger population. There are also snowball sampling and theoretical sampling. Again, snowball sampling in particular is quite an advanced statistical technique. There are classes taught at UMass by Krista Guile that look at snowball sampling and the statistics of it in greater depth. Quota sampling is a little bit funky. It can still be used by some online companies. If you ever in the future contract with a company, you need to understand what some of the limits are. Though in general, at this point in time, one of the things that we're finding is that quota sampling and other forms of non-probability sampling, if the weights are applied to them correctly, they can often be about as good as probability sampling, given some of the issues we've had over time with people not responding to even online surveys. So I'll leave aside much of the advanced discussion of this for more advanced survey courses, but just know that there are these different methods out there, and random sampling or even probability-based sampling is not necessarily always going to be used, nor is it necessarily always vastly superior. It depends a lot on some of the really detailed fundamentals of how these different surveys are done. Theoretical sampling becomes quite important when we talk about particularly doing case analysis, process tracing, other forms of more in-depth, what might be described as qualitative, or in some cases, in essence, analytical narrative type approaches. So there might be reasons why we're very interested in, say, understanding cultural enclaves. And so we don't need to go out and make our sampling frame be all communities. We might want it to only be certain types of ethnic communities with certain characteristics, and we want to study in depth inside that. So there are reasons to sometimes do theoretical sampling. The same whenever you're doing a lot of interview research. You might theoretically not want to understand everyone, but you might want to very carefully choose which types of people you're going to sample and which ones you aren't. So who is in essence, your frame, not having an even probability of getting all possible cases that exist within that universe. One of the things to think in mind when you're designing a study is whether the cases you're going to select are in fact potentially a universe or actually a sample. So for example, if you're using census data, this would be potentially considered a universe of cases, all possible Americans. Now, ironically, with census data, several studies have shown that, in fact, if we sample from the American population, we can get more accurate descriptive results on, say, income and preponderance or prevalence of certain characteristics of the population than if we conduct an entire census. This is in part simply because people get missed, undercounted, double counted with the way we try to do the census, and a well-designed sample can be more descriptively accurate. It's some interesting research worth looking at. There are some studies, such as Piketty's study of IRS returns, that do use an actual universe of cases. So he was able to get access to all IRS returns in a given year or a given set of years, for example. Now, there are statistical questions about whether we should treat that when we're describing those data or making inferences based on those data. How do we treat them? Do we treat them as the actual universe, or is it really a sample from all the returns that could have been turned in because we know there's some errors? Or do we treat a particular year as a sample of all the returns that have been turned in over a series of years? Same types of things when you're looking at certain types of, in essence, aggregate level data. So GDP at the country level, graduation rates at major universities. Again, we have questions. We're in essence getting the entire universe of actual universities that exist, at least if we're, say, looking at American universities where we've got a lot of census type data or universe type data available. But do we treat those as samples or not? Statistically is a question that requires some advanced consideration. How about things where we're looking at the legislature or certain regulations? Again, it's fairly easy to look at the universe, all possible policies, or all the years in which we have basically all states, right? So all 50 states, we can actually collect time series data and say, okay, did they have a particular policy in a given year or not? Yes, no, that could be a data set. Do we treat that as a universe or a sample? That might be closer to a universe, but how we treat it statistically is a different question. Some of you may be familiar with the Fox News/NPR finding from a few years back, where several studies found that people who watched Fox News had less factual knowledge about American politics than those who watched NPR. The Fox News viewers were by far the least informed. Now, if we wanted to go in and actually then study whether or not it's the factual content of the news coverage, we would again have to decide, do we look at all Fox News coverage? Do we take a sample from it? And to some extent, we might even ask, in a multi-method sense, whether or not this is even the correct question to be asking. As it turned out that Fox News viewers often did get information from other sources, and yet we're still the least informed. And so the question becomes, is it simply the content of Fox News, or is there something else going on with those viewers, the way they're screening out information, or the way they are paying attention to certain sources, as we discussed before in the sleeper effect, that actually makes them more or less likely to be accurate in terms of their political knowledge. Finally, anytime you're studying something like lobbying, there was a great article on lobbying of the Basel Committee, the Economic Committee. So that's really, if we know every single time that committee was lobbied, then we've got the universe of cases. So There are instances in which we actually can collect data on the universe of cases. There are cases like when we're trying to study a general population sample survey, obviously we're getting a sample. But even when you've got the entire universe available, sometimes you have to ask yourself, is this a universe or is this a sample?